Right, okay, so this is a collaboration between the Czech Technical University in Prague, MITRE, and the University of Huddersfield. And what is the context of what we are talking about today? So we know that cyber attackers are leveraging more and more AI techniques to increase their fire capacity. So basically what we're trying to do is to use new and advanced ways to find weak spots in networks. And a way which you can try to defend yourself as an admin of a network is playing red teaming and adversary emulation. So what you're basically trying to do is executing some controlled attacks in order to discover such weak spots so that they cannot be exploited by someone else. And for performing this kind of emulation or this kind of controlled attacks, there are two ways: manual tests, which has been used for a few years right now, but of course they are tedious, they are long, they are expensive, and you may lose some vulnerabilities. Or you can leverage on actually the same or similar AI techniques that would be used by an attacker in order to perfectly emulate their fire capacity and the way in which they would perform such attacks. And surprisingly, well, not surprising for us actually, planning is one of the techniques which has been exploited, and actually it results that it has been exploited by both sides. I don't think I need here to describe what is AI planning, but why does it play the role so well in adversary emulation or in red teaming or in attacking in general? Because, well, first of all, our computers, so the infrastructure in terms of software and hardware, is very prone to be represented as a plan, because you have a controlled environment and everything is formalized actually. And for instance, if you want to make a copy of a file, here we have what a plan for performing the task would look like. So you have actions that you can perform. Those actions will have preconditions in order to allow you to perform them, and will have effect. Basically, a plan. And of course, in planning, we've done also quite a lot of research in generating different and multiple plans for performing exactly the same task. So if you leverage planning in red teaming or in adversary emulation, you can actually exploit at the same time, or actually in different plans, but using the same infrastructure, a large number of possible vulnerabilities and a large number of alternative ways for performing attacks. So that's part of a very good plus of using planning for emulating attacks. And just to make sure that we are on the same page, we are referring here as planning at using PDDL kind of representation. So where you have a domain model, which here is represented on the top-hand side, and a problem model, which are provided to a general technique that can be space-based search or anything like that, for generating a plan which is a sequence of partially or completely ordered actions that allow you, given an initial state, so an initial condition of a network, to reach a given goal. It can be to compromise some hosts, for instance, according to what you want to achieve. And that leads us to the questions that we wanted to answer with this work, which is, how can a network be designed to reduce the automated planning capacity of a prospective automated attacker? So what we are looking at here is basically, how can I change my knowledge? And in this case, when I say knowledge, I'm referring to the problem representation, because we are assuming that you cannot change the domain model which is used by an attacker. But the question is, how can changes in our network be reflected in a problem model that makes the life hard for an attacker that wants to use planning to exploit the vulnerabilities of my network? So it's a kind of indirect way for slowing an attack down. And in order to find answers to these questions, we followed this process, this methodology. So we exploited the existing Caldera domain model that we'll see in a minute. And on the basis of that, we selected a set of representative scenarios that we can use for gaining insight and some deep analysis. We made a set of hypotheses in order to be able to check different hypotheses and different ways in which you can modify the model in a structural and principal way. And we made such modifications to basically test whether the hypotheses are confirmed or not. With regards to the Caldera domain, that was basically the natural choice because it has been already used in planning for the IPC in 2018. It is well known, and it represents basically a Windows domain, a Windows network, where you have quite a large number of predicates and actions that you can perform in order to simulate attacks to that network. In terms of the scenarios that we consider, we have taken two problems from APC benchmark because they were very different from each other. One was problem number 3, which is quite small. Problem number 8 is a bit more large and complicated. And we also generated a brand new problem, which is the one represented in here, which has been designed in order to be quite complex in the sense that it's a fairly large network for what can be dealt with planning techniques or for what can be dealt with in the Caldera domain. And the initial compromised host is host number 1. And then an attacker has multiple different ways to compromise all the different hosts or to ransom all the different hosts. So this specific problem was designed so that you have multiple choices in front of you, and that can affect the way in which the planning engine is working. And we also created 2 different domain models. So the original Caldera domain model, which was used in the IPC in 2018, where your main goal and the actions that you have are to compromise one host somewhere or to gain advantages somewhere. And we also designed a ransom domain model where the goal is to ransom all the hosts. So in this case, you can see that if you need to ransom all the hosts, the order in which you are ransoming the different machines has a very significant weight. So again, this can change significantly the importance of the models that you're dealing with and the importance of the knowledge on which you're working. And these are the hypotheses that we use. We basically divided them into 2 different sets, domain independent sets, which is basically, I am not a cybersecurity expert. I played that role very well. I'm not a cybersecurity expert, and only on the basis of planning knowledge, I try to think about some changes that can make the life hard for planning engines. Adding objects, adding predicates, and hoping for dead ends and these sort of things. The set on the right, so the domain-specific hypotheses, are instead taken from a perspective of saying, I know very well that the application domain, so the cybersec domain, and I'm thinking about changes which are reflected in something meaningful from a adversary emulator point of view. So adding complete new network, which are connected or separated to the original one, adding new domains, adding new admins, these sort of things. So a bit more elaborated, but domain specific. And on the basis, in order to test these hypotheses, we came up with a large number of modifications, basically. So each row here is a different modification that we applied. And this table is only to show you that it's extremely hard to identify a single change or a single modification that is testing a single hypothesis. So we needed to test multiple hypotheses at once. And in here you can see rows 1 to 8 are hypotheses that are tested by each modification. But on the basis of the conglomerated results between different tests, we can still derive some conclusions about whether an hypothesis is confirmed or not. And for each row in this table, we generated a large number of randomly modified instances to make sure that it was not by chance that the specific result was observed. And we selected to run these experiments 5 planning engines, basically according to their overall approaches, so the technique that they use to solve problems, and to their general performance, either expected or observed in recent IPCs. And as I was saying before, for each scenario, so for each row from the previous table, we generate 25 different instances. So considering that we have 3 problems that we are considering, each row corresponds to 75 instances in total that we are testing to make sure that things are as expected. And then, okay, 15 minutes time limit and 4 gigabytes per planning instance. And what are now the results on the original Caldera domain, so the one in which you don't have to ransom the whole network, but only to get some privileges? Now we can see that the different planners are reacting quite differently, of course, but there are some striking differences. So FF, probe, and BFWS seems to be quite sensitive to most of the changes that we observed. So adding unusable users, adding new domains, modifying the topology. Well, modifying the topology not much, but adding an additional network, all these things are having a very strong and significant impact on the performance of those planners. On the other hand, instead, Llama and fast downward stone soup are much more robust and tend not to be particularly affected by any of the changes in this domain. The main impact on Llama comes from adding unusable users, but that only leads to a slowdown of basically 1 second on average. And for fast downward stone soup, adding an additional network is doubling the time needed to solve a problem, but still this remains quite limited. Interestingly, there are some modifications for Llama that led it to improve its performance when compared to the control version of the models, so the unmodified models. And our intuition here is that there are some, these modifications allows you to generate plans in a different way, and this different way seems to be easier to be found by Llama, at least in that specific instances. And when we come to the ransom domain model, we observe that things are quite different for everyone. So first of all, these instances are harder to be solved. That, of course, because orderings come as an issue here. And we can also see that now, fast forward, probe, BFWS, they are still having significant issues, basically with the same kind of changes that we have seen before, a bit more marked in some ways. But now also Llama is showing some significant slowdowns when the topology is modified and when new domains are added. Also, but in a more limited way when you are adding an additional network. Fast downward stone soup is still the most robust, very likely because of its portfolio nature. But again, there are cases like adding additional network where things can be slowed down, again, just by a half, not in a huge way. So in summary, what is the outcome of a test that we perform? So the naive strategy of adding random objects is not very effective. So usually this is not exactly what you would perform. Adding to the network unusable users, so a limited detrimental impact, but in some cases that can work and that can be enough. New domains, so brand new domains, lead to mixed results, but in some cases you're getting planners which are faster, so that is a bit of a can of worm. Adding an additional network has the strongest general impact. So our suggestion of a take-home message would be that if you can create this sort of fictional network that can be either attached, that would be great, or just isolated from your actual and real one, that is the best strategy. And then, okay, here we have a summary of which hypothesis has been supported, rejected, and which are undecided because of mixed results. So in conclusion, we investigated how to support deception against automated adversaries, and we did that by exploring how modifying the knowledge can affect the performance of a fictional attacker using planning. We have identified a number of strategies or promising techniques that you can put in operation to slow down an attacker. And what we are planning for in terms of future work is to focus on laying honeypots. So basically in preparing traps or forcing paths for planners so that you can flag up that an attack is underway. And that's all. Thank you very much for your attention.